We're now going to be concerned with several topics which involve differentiation. That's to say, the process of finding the derivative of a function. And the first of these is implicit differentiation. The standard example for implicit differentiation is probably as follows. Consider a circle. Let's consider one of radius 2. Right. This has the equation x squared plus y squared equals 4. Huh? All right. And if we solve this for y, we find that y is equals to the square root of 4 minus x squared. Actually, plus or minus the square root. The circle actually can be broken down into the two halves, its upper half and its lower half, and you then get two functions. y1 describes the upper half of the circle. It's plus the square root of 4 minus x squared. y2 equal to minus the square root of 4 minus x squared describes the lower half of the circle. Now, if you differentiate either of these two functions, you do so as follows. The derivative of y1 is equals to 1 half 4 minus x squared to the minus 1 half times the derivative of 4 minus x squared, which is minus 2x. That's to say, this is equals to, canceling the 2 and the half here, it's equals to minus x divided by the square root of 4 minus x squared. Or, since square root of 4 minus x squared is y1, this is equals to minus x over y1. If we differentiate the second, we get, similarly, y2 prime is equals to minus 1 half 4 minus x squared to the minus 1 half times minus 2x, which is equals to, canceling the minus 2 and the half, we get x over the square root of 4 minus x squared. Right. And if I multiply now numerator and denominator by minus 1, I've got this, and now y2 was minus the square root of 4 minus x squared, so this is equals to minus x over y2. So that in either case, the function y1 has, for its derivative, it can be written as minus x over y1, and y2 has the same formula for its derivative, minus x over y2. Well, now this is really not too surprising. Consider x squared plus y squared equal to 4. If we treat y as if it were a function of x, then this is an equation. The left-hand side is a function of x, and the right-hand side is the function of x, which is 4. So, presumably, if these are two functions, 4 and x squared plus y squared, then they should have the same derivative. So what we can do here is we can differentiate the left-hand side of this equation, treating y as a function of x. And if we do that, we get 2x plus, now y is a function of x, so this is a function to the second power, so the derivative is going to be 2 times the function to the first power times the derivative of the function, dy dx. And this then should be equal to the derivative of 4, which is 0. Right? Now, if we solve this for y, we find that solve this for dy dx, we find that y dy dx is equal to minus x, or dy dx is equals to minus x over y. Compare here. Right? What this says is that since this equation can be broken up into two functions, then for either of those functions, the derivative is going to have to satisfy dy dx is minus x over y, and you can see that it does. Right? This is an example of what in general is called implicit differentiation. That's to say here, we've taken this equation in x and y and treated y as if it were a function of x. And since it can be broken down into the two functions of x, then for either of those two functions, we find that dy dx is minus x over y. What this means is that for any point xy, on the curve, the derivative at that point, xy, is given by minus x over y. All right, we'll now take a look at how to do that in general. All right, now here's the general picture with respect to implicit differentiation. Let's suppose that we've got an equation in x and y. The graph of an equation, if it's algebraic or trigonometric in character, is going to tend to be some sort of a curve, perhaps something like this. Right? That curve can frequently and usually be broken up into several pieces. The curve may cross itself, but we can break this particular curve here up, for example, into this piece here, which is a function of x. This may be y1, for example. Here's a second piece. y2 is a function of x. Here's a third piece here, from here to here. y3. A fourth piece down here. y4. And here's a final piece right here. y5. So that the graph of the equation can be broken up frequently into several pieces, each of which is a function of x. Now, the idea behind implicit differentiation is to take the equation in x and y and treat y as if it were a function of x. Right? So the second thing that you want to do here, well, first you start with an equation. The second thing you want to do here is to differentiate both sides of the equation. Treating y as a function of x. Right? If you've got two sides of an equation and the equation holds, then when you differentiate both sides, the derivative of the left-hand side should be the same as the derivative of the right-hand side, so you equate them. Right? Then the next thing to do here is to take all of the terms which do not have dy dx in them, and it's a good idea to use dy dx, for example, in your symbolism here, or something at least that distinguishes this from y, because y is going to occur in the resulting equation. So take all of the ones that do not have dy dx in them to the right. That's to say, subtract the ones that are on the left from both sides of the equation so that these end up on the right. All the others, which do, to the left. And you'll find that it's always possible to do this. Right? And then the next thing to do is to solve for dy dx by dividing both sides by whatever precedes dy dx, by the multiple of dy dx. This will always be possible to do if you've got some sort of an equation that's algebraic or trigonometric in character. And this will then give you an expression for dy dx in terms of x and y. And that expression will be valid at any point xy on the curve where there is a tangent and where it's not a multiple point, like here, for example, like so. As long as it's not a multiple point of the graph of the curve, and there is a tangent, for example, there's not a tangent here, there's a vertical tangent, say, if there's a tangent with a slope, then putting x and y into the expression for dy dx will give you the slope of the tangent, providing x and y are on the graph. Now, there's one thing that's worth noting here, and that is that if you take the equation in x and y, and you manipulate it algebraically somehow, multiply both sides by y or something like that, and now you proceed with this program, you will be able to do exactly what's outlined here, except for one thing. The expression that you get for dy dx is not necessarily going to be the same as what you would get if you would have not performed the algebra first. However, the expression that you get for dy dx will agree with a different expression at each point on the curve, and it will tell you the slope of the tangent at each point on the curve. However, this expression here for dy dx is not unique. There may be several of them. However, all of them are going to agree on the given curve that satisfies this equation in x and y. Okay, let's take a look at a specific example. Let's suppose we have the equation 3xy plus sine of x plus y is equals to y cubed. Now this is an expression which would not be easily solved for y. It probably couldn't even be solved for y at all in any reasonable fashion. However, we can assume that it has got some sort of a curve for its graph, and under that assumption we can treat y as if it were a function of x and differentiate both sides of this. All right, this left-hand side here, 3xy is a product, so the derivative is going to be the first 3x times the derivative of y with respect to x, plus the second y times the derivative of the first. Okay. Here, when you differentiate y, you've got to treat it as a function of x. Right. Plus, now this is a composition of sine of x plus y, so the derivative is going to be the cosine of x plus y times the derivative of x plus y, which is equals to 1 plus dy dx. And then this is we're going to set equal to the derivative of the right-hand side, and the right-hand side is y cubed. That's a composition. It's y to the third power. So the derivative is going to be 3y squared, and then times the derivative of y with respect to x. Right? The important thing is to always keep in mind that you're treating y as a function of x, and so when you differentiate, you have got to use the rule as if y were a function. Okay, the next thing to do now is to take everything that's got dy dx to the left and everything that doesn't to the right. And you'll always be able to do this. All right. It's not really necessary to prove that you'll always be able to do it. It's basically a consequence of the fact that the derivative is always going to multiply the algebraic quantities that are differentiated or not, one or the others. So that here, for example, if we take everything with dy dx to the left-hand side, we've got 3x dy dx. That takes care of this. And now we've got this dy dx times cosine x plus y. So we've got cosine of x plus y times dy dx. And then we've got this, so this is going to be minus 3y squared dy dx. And bringing everything else to the right here, subtracting 3y from both sides, we get minus 3y. And we've got this term right here, the 1 times cosine x plus y, so we're going to have minus cosine x plus y. Now, one could have saved some time here by just writing all of this in front of dy dx. That's to say 3x plus cosine x plus y minus 3y squared times dy dx equals minus 3y minus cosine of x plus y. One could save even more time if one had simply written minus 3y minus cosine x plus y over here, and then dy dx, and as you collect the terms that multiply dy dx over here, instead of writing them in front, you're going to eventually divide by them, so you may as well write them underneath. So 3x plus cosine of x plus y minus 3y squared. So this then gives derivative of y with respect to x as a function of x and y. So that, for example, a point that's on this curve, without examining it too closely, would be x equals 0 and y equals 0. Because then we've got 3 times 0 plus sine of 0 equals 0. So 0, 0 satisfies the equation of the curve. And at this point, then, dy dx is going to be equal to 3y minus cosine of 0, so that's minus 1. So at 0, 0, dy dx is minus 1 over 0 and 0 here, but cosine of 0 is going to be 1. So dy dx is minus 1 at this point, where the curve crosses this point. The derivative, or the slope of the tangent, is going to be minus 1. So there's the first example. Okay. Here's another example. Let's take 7x plus 1 over y plus x y squared is equal to y to the 4th power. Okay, well, to differentiate this, we've got, first of all, a quotient here. So the derivative is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared plus xy squared is a product. So it's going to be the first times the derivative of the second, which is 2y, derivative of y with respect to x, plus the second, y squared times the derivative of the first, which is 1. And this is supposed to be equal to the derivative then of y to the 4th, which is 4y cubed dy dx. Right? Now, again here, you can always trust that you can separate the dy dx terms to the left and the other terms to the right. Here, because this is a quotient, this quantity right here, it has dy dx in it, and if we write this as 7y over y squared, this quantity right here will have only a y term in it. So bringing this term here to the right, we get 7y over y squared, or 7 over y. Right? We've also got this term here. This should be minus 7 over y if we're bringing it to the right side of the equation. We've also got this term here, which is going to be minus y squared when we subtract it from both sides. That takes care of all of the terms that do not have a dy dx in them. So now the terms that do have a dy dx, we would want to bring them to the left, but we may as well just write them right underneath here, because we're going to divide by them eventually. Right? So what are they? On the left, this is minus 7x plus 1. Right? On the left here, this is going to be plus 2xy. So that takes care of this term here and this term here. And now we've got plus 4y cubed. Right? So this then gives you dy dx as a function of x and y. And again, any point xy that satisfies this equation, this will give you the derivative at the point xy. Now, let's note something here. If we had multiplied this through by y and then performed the procedure, we would not necessarily get the same formula here, nor would we necessarily get anything that you can make look like this. Let's try it. We have 7x plus 1 plus xy cubed would be equal to y to the 5th. All right? Differentiating here, we get 7 plus, this is the product, so it's the first times the derivative of the second, y cubed, the derivative is 3y squared dy dx, plus the second times the derivative of the first, so that's plus y cubed, and this is going to be equal to the derivative of y to the 5th, which is 5y to the 4th dy dx. Now collecting terms again, bringing everything that has a dy dx to the left and everything else to the right, we end up with minus 7 minus y cubed, and on the left-hand side here, multiplying dy dx, we're going to have 3xy squared minus 5y to the 4th. So here's an expression for dy dx, and here's another one. It's perhaps clear that you're not going to get this expression to equal this expression except for certain points. And it will equal it, though, for the points xy for which the original equation is satisfied. If a point xy satisfies this equation, then this formula will give dy dx, and so will this one. So there isn't really a unique formula here involved with implicit differentiation. There can be several possible formulas, but they will agree on the graph of the equation that's being differentiated implicitly. I want to point out one further thing here with respect to implicit differentiation, and that is that you can have an equation in x and y where x and y are considered to be functions of a third variable, or you can have equations in quite a few variables, all considered to be function of another variable, and differentiate implicitly, treating the various unknowns as if they were functions of a given variable. So this frequently happens with the variable t, which is time, or is used frequently to represent time. So let's consider, let's say, x cubed y plus cosine of x minus y is equal to y to the 4th. Okay? And now here we're going to treat x as a function of t and y as a function of t, and assume that these are differentiable. Then you can take this equation right here and differentiate it implicitly. You're going to end up with an equation. You will generally not be able to solve this equation for anything in particular. So that, for example, here we're going to get differentiating x cubed y. This is the first, x cubed, times the derivative of the second, which is dy dx. Dy dt here, huh? Y is a function of t. Plus the second, y times the derivative of the first. The derivative of x cubed now is going to be 3x squared, and keep in mind that x is a function of t, so we're going to have this multiplied by dx dt. Plus, now this is cosine of x minus y, so the derivative is going to be minus the sine of x minus y times the derivative of x minus y. The derivative of x minus y is dx dt minus dy dt. And now this is equal to the derivative of y to the 4th, which is going to be 4y cubed times the derivative of y with respect to t. Right. Here again, y is a function of t, so this is a composition. It's y to the fourth power. The derivative is 4y cubed times the derivative of y. Right? It's clear that other combinations such as this can be gotten. Huh? I mean, if we had x plus y squared is equal to z, where x, y, and z were all functions of t, then dx dt plus 2y dy dt would be equal to dz dt. And we would then have an equation as a result that relates the functions x, y, z, and their derivatives. Likewise, here the functions x and y and their derivatives. This is also called implicit differentiation. Right? And it has applications which we will be looking at very shortly. Okay, we next want to look at what are called related rates problems, and these are a type of problem where the rates involving several things are related by an equation or equations, and you want to know what the particular rates are. And so the first thing to do with a related rates problem is to write down all equations from the problem which hold at all times. Right? The problem will generally have some particular information that only holds at the time you're interested in, and also it will have some sort of a geometry or some sort of relationships that hold at all times, and the thing to do is to disregard the particular information for the moment and just write out all the equations that you can which hold for the problem at any time whatsoever. Right? And the second thing to do is to differentiate them. Implicitly. These equations supposedly hold it at all times, and so you should be able to differentiate both sides of the equation and get an additional equation for each one that you've started out with. So now you have twice as many equations as you started out with. Now it's time to put in these equations the values or numbers which only hold at the time of interest. If the original equations were in t, it's not a bad idea to indicate that this time that you're interested in is t naught. Right? And then the fourth thing to do is to solve for the quantities that you wish to know. Solve for the desired quantities. Now, frequently a problem will suggest to itself that there's only going to be one solution to this, and that you ought to be able to find out what the various rates are, or the various quantities are at a particular time. Right? If you write down all the equations that you know which hold at all times for this problem and follow this through on this, you can get down here and find out that you can solve for the quantities that you want to know. Sometimes, however, you'll find that you don't have enough equations to solve for the quantities desired, in which case it's a good idea to go back to step one and make sure that you've written down all the equations which hold for the particular problem. Right? Repeat the steps here then, differentiate them implicitly, put in the values which hold only at the time of interest, and solve for the quantities desired. This will become apparent as to what's meant by this when we look at several examples. let's look at a first example. Let's suppose we've got two airplanes. One's traveling east at 500 miles an hour, and let's suppose that it's 400 miles away from the airport here, if you want. And another one's traveling north at 300 miles an hour, and let's suppose that it's 200 miles away from the airport. So this is the speeds, and this is the distance. Okay, what we want to know then is at what rate are these two airplanes departing from each other? And all this information here is particular information at the time we're interested in. The general situation here is this, that if this is x, and this is y, and this is d, then at all times, x of t squared plus y of t squared is equal to d of t squared. That holds true at all times. If we differentiate this, we get 2x of t, x prime of t, plus 2y of t, y prime of t is equal to 2 d of t, d prime of t. Right. So then this then holds at the particular time that we're interested in here. And now what we want to do is to solve for d prime of t at the time we're interested in. Well, at the time we're interested in, we can cancel all of these 2's here, and we get x prime at the time we're interested in is 500 miles an hour. That's x at the time we're interested in is 400, so this is x prime, so 400 times 500 plus y prime, 200 times 300 is equals to d prime. So d at the time we're interested in times d prime at the time we're interested in. Now we can use this equation to find out what d is. D at the time we're interested in is equal to the square root of x of t squared plus y of t squared, which is, at the time we're interested in, is going to be 400 squared plus 200 squared. Right? So now we can now solve this for d prime. The rate at the distance is changing between them, and it's going to be equal to 400 times 500 plus 200 times 300 divided by square root 400 squared plus 200 squared. And this is going to be in miles per hour, because those were the units that we used. It's important to make sure that you use the same units throughout the entire problem. Okay, so there's the first example. Okay, a second example of related rates. Let's suppose that we have a balloon, and it's going to be a spherical balloon, which is being blown up at, let's say 5 cubic feet per minute. Air is being blown into the balloon at 5 cubic feet per minute, and we're interested in this balloon at the time when the radius of the balloon is 11 feet. It's a big balloon, and the question is, how fast is the radius changing? So this is the radius at the time we're interested in. Right? We want to know the rate of change of the radius at the time we're interested in. Right? The 5 cubic feet per minute, this is the volume, the rate of change of the volume at the time we're interested in. This balloon does not have to be blown up at this constant rate. However, if it is, all we really need to know is the time we're interested in, the rate of change of the volume is 5 cubic feet per minute. If the balloon was being deflated, then this would be a -5, right, to indicate that it was going the other direction. Okay. Now, what do we know about this? Well, we know that at any time the volume of a sphere is equal to 4/3 pi r cubed. So this holds true at any time. V of t is 4/3 pi r of t cubed. So differentiating this with respect to t now, v prime of t is 4/3 pi. Now the derivative of r cubed of t is 3 r of t squared times the derivative of r of t. And now we have two equations, the original one and the differentiated one. All right. Now we're ready to put in the information that we know. Right. At the time we're interested in, v prime is 5 cubic feet per minute. This is going to be equal to 4/3 pi times 3. The radius at the time we're interested in is 11, so this is going to be times 11 squared r prime of t. So consequently, we can now solve this for r prime at the time we're interested in. This is at t naught. It's going to be equal to 5 divided by 4 pi times the 3's cancel times 11 squared, 121. And now this is going to be in feet per minute. So that tells us the rate of change of the radius at the time we're interested in. Well, let's look at a slightly different problem with the same idea. Let's imagine that we've got an oil slick that's formed by oil pouring at the center of a circle here, and that this slick has a certain thickness. And we want to know then what is the rate at which the radius is changing at a time t naught. What is this? Well, I'm going to change the problem slightly. Let's consider a simpler problem. Let's say that this is a pancake which is forming and that its thickness is always 1/4 of an inch thick. And let's suppose that we're interested, the pancake is being poured, let's say, at 2 cubic inches per minute, per second here. And we're interested in knowing how fast the pancake is increasing when its radius is equal to 3 inches. Okay, now, at all times for this particular problem, the volume of the pancake is equal to, it's 1/4 of an inch thick at all times, so 1/4 becomes part of the general picture here, and then the area of this is going to be pi r squared. So this is true now at any times t. V of t is equal to 1/4 pi r squared of t. So our volume now for this pancake has, for its derivative, v prime of t is 1/4 pi times 2r of t, r prime of t. And now we're ready to put in the data that we know at the time we're interested in. The rate of change of the volume at the time we're interested in is 2. This is equal to 1/4 times pi times 2. The radius at the time we're interested in is 3. And then we have r prime at the time we're interested in. And now we can clearly solve that for r prime at t naught. It's going to be equal to, dividing by 2 here, I'm going to get 1 over 1/4 pi, or 4 over pi times 3. So this is the radius at the time we're interested in, the rate of change of the radius at the time we're interested in. And this is going to be, again now, in inches per second, because the original quantities were in inches per second. So there are 2 examples of related rates involving circular type objects, a balloon and an oil slick or a pancake. Another example of related rates. Here, as elsewhere in calculus, we'll generally be using geometrical type problems, but in other areas where mathematics is used, there will be problems that are not particularly geometric. Let's consider one as follows. Let's suppose that we've got a cone here. You can think of this as one of the cones that holds liquid that you can drink out of. And let's suppose that it's got a radius at the top here of 3 inches and a height of 5 inches. And liquid through a straw is being removed from this at, let's say, the rate of 2 cubic inches per second. And what we wish to know is when the height here is, say 2.5 inches high, when it's down to the level of 2.5 inches high, what is the rate of change of the height? How fast is this going down? Right. Now, all of this is specific information with respect to this cone, except for the fact that the shape of the cone is 3 by 5. So if this is r at any times t, and this is h at any times t, then we have that r of t over h of t is 3 to 5. So r of t is 3/5 h of t at any time t. Right? We also have the volume at any times t of the cone is 1/3 the area of the base times the height. So that's 1/3 pi r squared of t h of t. So here we've got 2 equations now that hold at any time t. Right? There don't seem to be any others, so let's begin to work with these. If we differentiate this, we get r prime of t is 3/5 h prime of t. And if we differentiate the second equation, we get v prime of t as 1/3 pi. And now this is a product. So the derivative is the first times the derivative of the second plus the second h of t times the derivative of r squared, which is 2 r of t, r prime of t. We wish to know what is h prime at the time we're interested in. Okay, now we've got the equations and the differentiated equations, and we now can begin to put in the particular values that hold true at the time we're interested in. So that, for example, v prime at the time we're interested in is -2. That's v prime at t naught, because the volume is decreasing at the rate of 2 cubic inches per second. So that -2 will be equal to 1/3 pi. And now r prime at the time we're interested in. Well, h at the time we're interested in, r at the time we're interested in, we can get from this fact right here. It's 3/5 of the h at the time we're interested in. So this is going to be 3/5 of 2.5. And we now wish to square that. H prime at the time we're interested in, that's what we wish to know. H at the time we're interested in is 2.5. R at the time we're interested in, we already got, is 3/5 of 2.5. So times 2 times 3/5 times 2.5. And r prime at the time we're interested in. Right? So we're left with this. Now we know that r prime at the time we're interested in is 3/5 of h prime at the time we're interested in. So if we replace this with 3/5 h prime at t naught, we will then have one equation which involves h prime of t naught, and it's easily seen that this equation can be solved for h prime at t naught by taking the multiples of h prime of t naught and dividing. Right? In particular, what? H prime at t naught is going to be equal to -2 divided by 1/3 pi times 3/5 times 2.5 squared plus 2.5 times 2 5 times 3/5 times 2.5 times 3/5. So this then gives you a numerical answer for h prime of t naught for this particular problem. Another example involving related rates, this time one using trigonometric functions. Let's suppose that we've got a lighthouse here that's, let's say, 100 feet away from shore, and the beacon of this lighthouse turns at 2 revolutions per minute. We want to know how fast the beam is going when it crosses the shore right here. Right. Well, if this distance here is x at any time t, this is always a fixed 100. So the 100 here is good at any time t. And we have, if this is theta, it's a function of t, and x of t over 100 would be the tangent of theta of t. Now here, you cannot, with calculus, use revolutions per minute. You need to rewrite this as the fact that this is, in radians, is 4 pi radians per minute. Radian measurement is needed for the calculus trigonometric functions. All right. So this is an equation now that's true at any time. Differentiating, we get x prime of t over 100 is equals to secant squared of theta of t times, this is the composition tangent of theta of t, so it's secant squared of theta of t times theta prime of t. And now, at the time we're interested in, this needn't be turning constantly at 2 revolutions per minute. It only needs to be turning it at the time we're interested in. We know that at the time we're interested in, we want to know x prime of t. It's going to be equals to 100 secant squared. This is going to be 1 over the cosine of theta of the time we're interested in squared times the rate of change of theta at the time we're interested in, which is 4 pi. And now, the angle that we're interested in here, theta, this is cosine squared. The angle we're interested in is 0 degrees. So the cosine of 0 is 0, so that this is 400 pi is the rate that x is changing. If this 100 was in feet, which was what was originally intended here, then this is going to be in feet per minute. If we wanted to know how fast the beacon was moving down the shore here at a different angle, you would simply put that particular angle that you were interested in here, and you would find out how fast it was moving by taking the cosine of that and squaring it, and then dividing that into 400 pi. Look at the last example here with respect to related rates. Let's imagine that a ladder is leaning up against the wall. It's a 10-foot ladder. It's leaning 8 foot up the wall here and 6 foot away from the wall. And let's imagine that the bottom of the ladder is moving, is being moved at 2 feet per minute. What we want to know is at what rate is the ladder moving down the wall at this time. All right. Well, the size of the ladder doesn't change, but if this is x here, x of t changes, and y of t, if this is y, changes, and we have x of t squared plus y of t squared is always equal to 10 squared, 100. That's true at all times. So we get that 2 x of t, x prime of t, plus 2 y of t, y prime of t, is equal to the derivative of 100, or 0. Right? And now if we solve this for x prime of t, we get that x prime of t is equal to minus y of t, y prime of t, divided by x of t. X prime, I want to solve this for y prime of t. So y prime of t is equal to minus x of t, x prime of t, divided by y of t. So this then gives an equation for y prime of t at any time t in terms of x, x prime, and y prime. At the time we're interested in, y prime at the time we're interested in, x is 6, so it's going to be minus 6. X prime is 2, and y is 8. So it's going to be equal to minus 12/8, or minus 3/2 feet per minute. The units that were used throughout the problem. So it's the minus indicates that it's falling downward here, and the rate is 3/2 of a foot per minute. It's interesting to note the following, that if you pull this ladder forward here until it is almost lying on the ground, then y of t is going to get very close to 0 here, and the rate y prime of t is going to get very large. It will not actually be possible to keep this ladder up against the wall here when y gets very close to 0. Because if you could keep it up against the wall, then the speed that it would be falling at would get to be immense. We now wish to look at the new subject matter, the subject matter of differentials. Differentials are defined to make the notation dy dx, which looks like division, actually become division. But they serve other purposes besides that. Here's the basic idea. We start with delta x. This is to be any number whatsoever, but usually you consider it to be a small number. Right? It's the change in x. Right? This is one symbol that represents the change in x. Given delta x, we define delta y to be the change in y. That's to say it's f of x plus delta x minus f of x. And the thing to note here is that delta y depends on two things, x and delta x. So it's not simply a simple symbol here. All right? These two quantities here are sometimes called increments. So this is the increment in x, and this is the increment in y, or change in x and change in y. dx, the differential x, these are going to look at the differentials. dx is nothing more than delta x. That's to say it's any number whatsoever. It's frequently written with a dx when dy is present. dy is going to be the derivative of f at x times dx. That's to say times the change in x. And again, dy depends on both x and delta x. So it's not a simple quantity. It depends on what x is and what delta x is, just as delta y does. The picture here is this. If you have a function like so, and this is x, and this, let's say, is x plus delta x, then here's the value of the function at x. Here it is at x plus delta x. And so that the change, delta y, is the difference between the function at x plus delta x and the function at x. If we draw the tangent to this curve here, and if we look at the value on the tangent line, the change between the value of the function at the point and the value of the tangent line is dy. It's easy to see that if we take the derivative and we multiply it by delta x, then this magnitude right here will be dy. It can be either larger or smaller than delta y, but the usefulness of differentials frequently is due to the fact that delta y is approximately equal to dy. We put an equality sign with a dot above it for approximately equal. The other thing that makes differentials useful is this, and that is that f of x plus delta x, the value of a function at a new point, is approximately equal to f of x plus f prime of x delta x. Or it's equal to f of x plus dy. It's exactly equal to f of x plus delta y, and it's approximately equal to f of x plus dy. And sometimes it's easier to use dy instead of delta y for approximating the function. And sometimes this is also useful for theoretical purposes. One can note here now, in terms of this notation, that dy dx is now a quotient. This is equal to f prime of x dx over dx, which is f prime of x. So we've been able to write the dy dx as a quotient here. However, you should keep in mind that this quotient depends on x and on delta x. The numerator and denominator do. However, when you perform this quotient here, then it's clear that dy dx only depends on x because the delta x's cancel. Second thing to note here is this, that this approximation is really quite good for small values of delta x. If we take and we look at f of x plus delta x minus f of x minus f prime of x dx, or delta x, if we look at this minus this, look at the difference between the two. This is equal to epsilon, a function of delta x, times delta x, where epsilon of delta x approaches 0 as delta x approaches 0. So the approximation, not only does this approximation get very good, but even if you divide it by delta x, you still have something that approaches 0. And that's just simply because if we divide both sides of this by delta x, we end up with f of x plus delta x minus f of x, I'm dividing by delta x here, minus f prime of x, and this indeed is equal to some number epsilon, which depends on delta x, and does go to 0 as delta x does, because this approaches the derivative, and so the left-hand side of this goes to 0. The right-hand side, epsilon of delta x, also goes to 0. So that the approximation, f of x plus delta x, approximately equal to f prime of x delta x plus f of x, is a very good one for small delta x. It not only gets close, but it gets so close so that if you divide by delta x, the resulting quantity still approaches 0. Okay. We'll look at a couple of applications next of this. Okay. Today's calculators make the use of differentials more theoretical nature than a practical one because you can compute a lot of things very accurately with a calculator. However, let's look at how one could use a differential, for example, as follows. let's suppose that we've got a sphere here, water tower perhaps, with a radius of 20 feet. All right. And suppose that we wish to paint this, and we wish to apply, let's say, a 25th of a foot thick paint, a coat of paint, a 25th of a foot thick. Well, if we wanted to know how much paint we needed all together here, what we really should do is we should look at the volume of the sphere of size 20 and a 25th, and subtract from that the volume of the sphere of radius 20, and this will tell us the amount of paint that's needed on here. So this is the exact amount, and this is what? This is delta V, where R is equal to 20, and delta R is equal to 1/25th. And V, as a function of R, is 4/3 pi R cubed. So we would take, to compute the actual amount of paint, we would take 4/3 pi times 20 and a fifth cubed minus 4/3 pi times 20 cubed. And this would give you the actual amount. So this is delta V. Well, delta V is approximately equal to dV. And dV is equal to 4/3 pi times the derivative of V with respect to R, 3R squared. It's the derivative of V with respect to R, dr. Here. dV is equal to V prime of R dr, thus making V prime of R a dV over dr. And this is approximately equal to now delta V. So this says that delta V for our particular problem is, canceling the 3's here, 4 pi times 20 squared times 1/25th. Right? Or what? 20 times 4. 20 squared is 400 divided by 25 is 8. So 32 pi cubic feet of paint. Right? And by knowing how many cubic feet are involved with a gallon, or cubic inches involved with a gallon, 231 cubic inches is 1 gallon. You could compute the number of gallons of paint that would be used to paint this particular object here. And it would be reasonably accurate. You can check that if you take and compute the exact quantity, it's going to be only slightly off from the quantity computed here. In fact, this is somewhat interesting here. The surface area of this sphere is 4 pi R squared. So this is the area of the sphere. That's 4 pi R squared. And this is the thickness of the paint. So you could get a sense that if we took the area of the sphere here and divided and multiplied by the thickness of the paint, we should get approximately the amount of paint that's needed to paint the sphere. One might even believe that that's the exact amount, but it's clear that as this goes out a little bit, there's just a slightly more paint needed to paint the outer edge when it's out 125th of a foot than there is to just paint directly on the surface. Okay, we wish to take a look at another example of differentials here. Here is an example of how you might use differentials to approximate the value of a function. We want to take a look at how you can use differentials to find a numerical value of a particular quantity or approximations to it. Now, the differentials actually are more of theoretical use today because of the calculator and computer. We'll look at shortly a method that gives you better and better approximations. The differential will give you just one better approximation to a particular quantity. Let's suppose, for example, that we wanted to approximate the cube root of 25.
Right. Well, one way to do this then is as follows. Let's let y be equal to the cube root of x. Right? If this is the cube root of x, then we can find the cube root of x very easily for x equals 27, but we're interested in 25. So what we're going to do is we're going to look at the value on the tangent line rather than the value of the function. And since cube root of x is fairly flat, this is going to be a pretty good approximation to the cube root of 25. That's to say, we let f of x be equal to the cube root of x, or x to the 1/3. Then the derivative of f is going to be 1/3 x to the minus 2/3. Right? We're going to use the approximation f of x plus delta x is approximately equal to f of x plus f prime of x delta x. Right? Where here delta x or dx, sometimes this is written dx, is going to be minus 2. We're interested in going 2 units back here from 27. X is going to be equal to 27. And so then we get that f of 25, or the cube root of 25, is approximately equal to f of 27, the cube root of 27, plus f prime of x, delta x. So delta x is minus 2, and f prime of x is 1/3 cube root of x squared. So when x is 27, the cube root of x is going to be 3. 3 squared is going to be 9. So this is going to be 1/3 times 9. Or the cube root of 25 is approximately equal to 3 minus 2/27, or 2 and 25/27. Now that's a pretty good approximation if you can check it even with your calculator. See what the calculator gives for the cube root of 25, and this should be approximately it. Right? So this is how a differential could be used for a particular approximation to a given number. Let's take a look at a couple of other examples. A similar one here. Let's suppose we wanted to compute the square root of 19. Right, well, here the square root of x looks something like this. Right? The value at 16 is easy to compute. It's 4. Right? We want the value at 19. So if we let f of x be equal to the square root of x, and x we're interested in is 16, and dx here is 3, or delta x is 3. F prime of x is 1/2 x to the minus 1/2, or 1/2 square root of x. So the square root of 19, which is f of x plus delta x, is approximately equal to f of x plus f prime of x dx. That's to say it's approximately equal to f of 16 is 4, square root of 16, plus the derivative at 16 is 1/2 times 4, 1/8, and our delta x now is 3. So 4 3/8 is an approximation to the square root of 19. Right? You can notice that since the tangent, it's the value on the tangent line, and since the tangent line lies above the graph here of the square root of x, it's going to be a little bit too large. Right? Let's take a look at another example. Let's suppose that we wanted to approximate 1.01 to the 60th power. Right? Well, if we consider the function f of x is x to the 60th, it looks like this. Here's 1. It's very steep here. Right? If f of x is x to the 60th, we know the value at 1. That's 1. Right? F prime of x is 60x to the 59th. Right? Our delta x here that we're interested in is dx is 0.01. So that's 1.01 to the 60th power is equals to f of x plus delta x, which is going to be approximately equals to what? X is 1, dx is 0.01, so this is going to be 1 to the 60th. F of x plus f prime of x delta x, so plus 60 times 1 to the 59th times delta x, which is 0.01. So this is equal to 1.6. Right. Now, here the graph of the function lies above the tangent line, so that this approximation is going to be a little bit too small. You can give this particular example here an interpretation. Imagine that you put $1 in an account, or invested it, at 1% interest per month for 5 years, for 60 months. Right? Well, then 1.01 to the 60th power would be the amount that you'd have at the end of 5 years. This is going to be approximately $1.60. Right? This approximation is a straight line approximation on the tangent line, and what it amounts to is computing this as if you had received simple interest of 1% on your dollar 60 times. So you can see that the approximation, the linear approximation here is simple interest, and it's the approximation to compound interest like so. This compound interest is clearly going to be a little larger. So we want to take a look at interpolation, and you're probably familiar with this with respect to interpolating values on a table. The basis for the idea of interpolation is similar to triangles. We're going to use this to get a first approximation to the solution as to when a particular function is 0. The reason for wanting a solution to when a particular function is 0 goes something like this. Frequently, you want to know when two functions are equal. Well, you can always reduce this to the problem of when is f of x minus g of x equal to 0 then, huh? And if this is the function capital F of x, then what we want to know is when is f of x equal to 0. Okay? Now, the situation that frequently occurs here is that we've got the 0 trapped between the two numbers a and b. So if this is a, this is bf of b, the point bf of b, and this is a f of a. Right? One of these is below 0, the other one is above 0. The function does something like so, perhaps, and we want to know where it crosses 0. That's to say, when is f of x equal to 0? Well, this is going to be the point 0. I'm sorry, this is going to be the point x 0 here, huh? Right. Well, actually, what we want to do is we want to look at the line connecting AF of A to BF of B. And the interpolated value here is going to be the point x0. And the way in which what interpolation is based on is the fact that you've got similar triangles here. This large triangle here is similar to the smallest triangle here. So if we wanted a first approximation, and for this function is not going to be particularly good, but if we want one by interpolation, that's to say by determining where this line meets the x-axis, you can, if you do this frequently, you can probably get familiar with what you need to do. If you don't, however, what you can simply do is write down the similarity between these two triangles here, so that, for example, this height right here is f of b, right, divided by b minus x. Right? This must be equal to f of b minus f of a divided by b minus a. Right? And we want to know what the value x is, and we can simply solve this for x. We get what? B minus a over f of b minus f of a is equal to b minus x over f of b, so that this times f of b is going to be b minus x, so that x is going to be equal to b minus this. This is the solution of this like so. And this says, for example, that the value x, for the value x, you take the value f at b and you back up. You subtract so much. You take the value at b, the value b, and you subtract f of b times this quantity right here. Right? If you have a good sense for this, you can do it naturally. Otherwise, it's a good idea to write the equations down. It's not a good idea to memorize the equations, of course, because this is just the equation for similar triangles. And then this gives you the interpolated value here. This is the same type of interpolation that you do if you know that a function at one point a is af of a, and at b it's bf of b, and we want to know what the value is at some point c in between. That's to say, we take the value on the line and use these two similar triangles here to compute what the interpolated value at the point C would be if the graph, let's say, went through here smoothly like so. It's the same principle. Okay, we want to take a look now at a method for approximating where f of x equals 0. Right? Which is known as Newton's method, because of course it was developed by Isaac Newton, and sometimes it's called Newton-Raphson method. And it has the advantage that it can be used over and over again, providing it's going to work. And it's frequently the type of method that a computer will use, iterating over and over again until it gets closer and closer approximations to the number x where f of x equals 0. Let's take a look at the situation here. Let's suppose that we've got a function f of x. Right. And we want to, we know, let's say that at a it's negative and at b it's positive, or vice versa. And we want to find out where it is equals to 0. Well, if we take a first approximation to this c, perhaps gotten by interpolating, right? Newton's method simply says this. For a second approximation, let's call this approximation x of 0. And for a second approximation, take the value where the tangent line crosses the x-axis. Right? So if we're given x0, we want to know, where does this tangent line cross the x-axis? Well, it's going to cross at a point x1, 0. Right? And x1 is going to be your second approximation. You can then repeat this process here by taking the value at x1 and finding where the tangent line at x1 crosses the axis. This will give you repeated approximations, which hopefully will get closer and closer to the solutions to f of x equals 0. So given x0, we want the tangent line through the point x0, through the point x0 f of x0. Right? And this is going to be y minus f of x0 over x minus x0 is equal to the derivative at x0. This is the slope for point x0. y on this line, and this should be equal to the derivative at x0. All right. Now what we want to do is we want to find out where that crosses the x-axis. That's to say, what's the solution to this when y equals 0? What is x? All right. And so when y is equal to 0, we're going to get minus f of x0 is equal to f prime at x0 times x minus x0. Or minus f at x0 divided by the derivative at x0 minus here is equal to x minus x0, or x is equal to x0 minus f of x0 over f prime of x0. Right? Now, clearly, one of the things we have to suppose here is that f prime of x0 is not 0, otherwise this would not cross the x-axis. This will then give us x1, a second approximation. And in general here, you can just simply iterate this. x2 will be x1 minus f of x1 divided by the derivative at x1. And in general, xn plus 1, if we've got xn, will be xn minus f of xn divided by the derivative at xn. So here then is a formula for getting a next approximation, right, to the solutions to f of x equals 0 when you've got a previous one. Now this is a nice situation here in the sense that it just involves this quotient, right, and the difference, and so a computer can use this over and over again and get better and better approximations, providing the thing works. Now there are situations in which it doesn't work, and there are also criteria for when it works, but we're not going to be too concerned about them right now. An example of where it wouldn't work would be something like this. Right? If this was our first approximation here, if we follow the tangent line down, we're going to get something like this, which is perhaps going to send us further astray, and further astray, and further astray. So that if this was our first approximation, this would be the second approximation, this would be the third, and it's clear we're not getting any closer to where this is equal to 0. Right? Okay, however, when this does work, it tends to work very well and very quickly and give you a good approximation after a few steps to the value of the function when f of x is, the value x where f of x equals 0. We want to take a look now at how Newton's method can be used. Let's again look at the problem of approximating the cube root of 27. The cube root of 25, cube root of 27, of course, is no problem. The cube root of 25. All right. Now, in order to use Newton's method to approximate this, we need to find some function, f of x. Right? So that f of x is equal to 0 at x equals the cube root of 25. Well, I want to find this. This is a considerable difference here between this and using differentials. So a simple example of a function which is going to be 0 when x is 20, when at the cube root of 25 is x cubed minus 25. Right? So that f of x be equal to x cubed minus 25, and it will be 0 at the cube root of 25. Now let's take a look here at the function. Right? It's going to be 0 somewhere between 2 and 3, namely at the cube root of 25. And it looks something like this. Right? The value of the function at 2 is 8 minus 25, or minus 17. The value of the function at 3 is equal to 2. So at 3, the value of the function is 2. Now we could use interpolation here to find out We could use interpolation to find out where a line would cross here, but let's just begin with 3 here and start using Newton's method, taking the point 3 to 2, right, and tracing the tangent line down. So our first estimate here is x naught is equals to 2. Right? And then for the x1, the second estimate, that's going to be where the tangent line crosses the x-axis. x1 is equal to x0 minus f of x0 divided by f prime of x0. Mention that this formula for getting the next term in terms of the previous one is worth remembering. Right? So that x1 here now is going to be equal to 2 minus, well, we need the derivative of f. F prime of x is 3x squared. So that we're going to take this at 2, let's say 27 minus 25, is 3, x0 is 3. We want to take this at 3, which is 2, and divide by the derivative at 3, which is 27. So here we get the same approximation that we got using differentials and the cube root. So that x1 is equals to 2 and 25 27s. However, here we can repeat this over and over again. So now we can get x2 if we want. It's going to be equals to x1. x1 is 2 and 25 27s minus the value of the function at x1. That's going to be 2 and 25 27s cubed minus 25 divided by the value of the derivative at x1, which is going to be 3 times 2 and 25 27s squared. Now, not being a calculator here or a computer, I'm not going to actually compute this number here, but it's clear that one could get this to however many decimal places they wanted and use this x2 then to get an x3 and continue doing this until you got as close as desired to the value of the cube root of 25. So here's an example of using Newton's method to approximate a particular number. I'll do one more example, similar to the last one, and similar to the one that was done using differentials. Let's try and find, for example, the square root of 19 using Newton's method. All right, so we need to find a function f of x, so that f of x is equal to 0 when x is the square root of 19. And f of x equal to x squared minus 19 should do the trick. So our function f of x looks like this. Right? It's the parabola here, x squared minus 19. And we want to know when it's equal to 0. Well, we know the square root of 19 is somewhere between 4 and 5. Huh? And let's use 5 here. Now we could interpolate, right? The value of the function at 4 is minus 3. The value of the function at 5 is 25 minus 19, or 6. So we could interpolate here to get a first approximation. But actually, if we stay on the right side here, 5 will give us as good an approximation as any. So let's let x0 be equal to 5. Okay. Then we need f prime of x. That's 3x squared. And then x1 will be equal to x0 minus f of x0 over f prime of x0. So that will be equals to 5 minus f of x0, f of 5 is 6. F prime at x0, f prime of 5 is going to be 3 times 25, 6/75. Right? So 5 minus 6/75 is the next approximation on the tangent line here. Okay? A second one, x2, right? We take x1 minus f of x1 over f prime at x1. So we would need to take 5 minus 6 over 75 minus, divide a function at this point, 5 minus 6 over 75 quantity squared minus 19 divided by the value of the derivative at the point. 3 times 5. Oh, f prime of x is 2x. Right? So that this should be 2 times, let's make this correction here, this should be 2 times 5 or 10. So down here this should be 5 minus 6/10. This should be 5 minus 6/10 minus 19. And now we have 5 minus 6/10 times 2. Okay, so x1 is x0 over f of x0 times f prime of x0. F of x is x squared minus 19, and f prime of x is 2x. So this is 5 minus, the value of the function at 5 is 6 over 10. Right? And then x2 is gotten like so. Right? To get x3, you take this quantity right here and put it back into this formula like so. All right? So that in general here, xn plus 1 is going to be xn minus, now our function is x squared minus 19, so xn squared minus 19 divided by 2xn. So this is something then that a programmable calculator or computer can continue to iterate and get better and better approximations for the square root of 19. Or for whatever other quantity is desired using Newton's method.